So, in this lecture, I am going to talk about commutator algebra, and commutator algebra play a very important role in quantum mechanics, especially when we have to deal with the matrix formulation of quantum mechanics. So, let us define a commutator. So, if I am having two operators, A and B, they are the two operators such that if they are enclosed in square bracket and separated by comma, then this is the mathematical representation of commutator relation, and it is equal to AB minus BA. Also, then this is the definition of commutator. Also, if I talk about BA, then it can be written as BA minus AB. Now let us discuss the certain properties. So consider AB commutator, and it can be written as AB minus BA, and it can also be written as like this if I take minus common, and if I use this here, then it will become minus BA, right? So that means commutator of AB is negative of commutator of BA. Then there is another property about which I am going to talk about. This is one property. So if commutator of two operator is 0, then we can say that operator A and B are set to commute. That is, A and B are compatible with each other, and this results that AB is equal to BA. Next property is any operator commute with any constant. Here these operators are nothing but they are basically matrices. So if I take an operator and if commute with every constant, so for that let us consider this commutator, and this commutator must be equal to 0. That's the meaning of it, that it will commute. Also, if I am taking it like this, then it can be written as A and B, or A can be taken outside AB. It can be expressed in this way, and let us try to do some mathematics for it. Say I am having a commutator like this, then it can be written as AB, comma is not there because it gets multiplied, minus AB. Since A is the constant, so it can be taken from here and from here, so it is A can be taken outside, so it is AB minus BA. So here I can say that it is AB. So hence I can prove this here also. Then next property is that any operator A commute with its own square. That is A square, which means that A, it will commute, means it must be equal to 0, and let us try to prove it. So A square minus A square A, and it can be written as A minus A, and all looks identical, so that means the result will be 0. Then next is a very interesting result. And if not if, but an operator A commute with any function of A. That is, if we are having a function of A operator, then its commutator with that operator is always 0. That's the meaning of it. And let us try to understand it by taking some example. I am considering a e raised to power p into p operators, and exponential, as I know that exponential function can be written in this form: n varies from 0 to infinity, and p raised to power n over n factorial. So keeping this in mind, what I can do, I can write down here n 0 to infinity p raised to power n over n factorial into p operator, and here it's a constant, and constant can be taken outside the commutator. So I can also take summation outside. So 1 by n factorial. So I am expressing it in this way. So now it is, if I put values and 0 first of all, then it will be 1p. 1 means identity. Then plus pp plus 1 by 2 factorial (1 by 3 factorial), and so on. As I know that it's a constant, identity means it's a constant, so it is 0. It is also 0, and all are will be 0, as we know from earlier discussion. Right. Then try to find out the commutator of position and momentum. Or I will talk about it later, but is the next property that A operator, B operator plus C operator plus D operator and so on, it can be expressed as AB operator plus AC operator and so on. Sorry, not so on, but AD operator. Commutator of this and so on. For this, let us take an example that if I am having A, B plus C, then how things will change. It is A, B plus C plus B plus C. Sorry. minus B plus C into A. So if I try to simplify it, it is AB plus AC minus BA minus BA and CA. So let me rewrite them together, plus AC so it is AB operator plus AC operator. So in this way I can prove this also. Then next property is regarding the Hermitian conjugate of commutator. So it is, I am having this one, and it is B commutator A, B dagger in this. Let me try to prove it. It is AB minus BA and whole dagger. It is AB dagger minus BA dagger, and it is B dagger A dagger minus A dagger B dagger. So that means it is B dagger A dagger. That's commutator. So that means I can prove this in this manner. Then if I am having A, B, C commutator, it can be written as A, B, C plus B, A, C. Let me try to prove it. How this will happen? Say it is A, B, C. Its commutator can be written as it is A, B, C minus B, C, A. Right? So what I will do, it is A, B, C. I will do one thing. I will add this quantity and subtract same quantity. This quantity is subtracted and this is added. So overall equality will not change. If equality will not change, then let me do one thing for this. If I first of all I will try to look at these two terms. From these two terms C can be taken outside, and since they are matrices, it can be taken this side. So it is C and it is AB minus BA. Similarly, I can take say B from here. So it is AC minus CA. So I can express it as AB commutator into C plus B and then AC. So hence I can prove it. Similarly, there is another property. Let me talk about that. That property is, it's also relating to this, that in the similar manner, I can see that if I am having A, B, C commutator, it can be written as A, B, C commutator plus AC. We can prove this in this manner as we have did here. Similar manner it can be proved. Then next is the Jacobi identity. a very important identity. In Jacobi identity, it is BC, its commutator of BC and its commutation with A, plus similarly BCA, ABC, then BCA, then CAB. I have to remember this in this way, means ABC, then BCA, then CBA. I have to remember the things in this manner, right? So plus CB, not CB but CAB, so this must be equal to 0. This is Jacobi identity, and let us try to solve this Jacobi identity. Say I am having plus BCA plus CAB. I can express it as A BC minus CB plus B into CA minus AC plus C into C comma AB minus BA. So it is A, sorry, I have not placed symbol of operators here to put it all. So it is A BC minus CB and BC minus CB into A, it's minus, plus BCA minus AC minus CA minus AC into B plus CAB minus BA So this after simplification, sorry, this is C and this is minus C, not minus C, but it should be AB minus BA into C. So let us open all these. So it is A BC minus ACB minus BCA minus plus CBA plus BCA minus BAC minus CAB plus ACB plus CAB minus CBA, and then operate this. So it is minus ABC plus BAC. Right, so this will cancel out with it, and ACB, it is ACB and it is ACB, so one is positive and another is negative. Then BCA is minus and it is BCA, yeah, it is plus, so both will cancel. CBA is this CBA, so one is plus and another is minus, then BAC. This is BAC and BAC. Sorry, it is BAC, both will cancel, and yeah, it is this one yellow. Yeah, it is ABC, so both will cancel, right? Then BAC, yeah, both will cancelling. So here BAC and BAC both will cancel, and then CAB and then CAB. So all the terms will cancel out, and the resultant will be 0. Hence, Jacobi identity will be proved. Then next I will talk about commutator of position and momentum. Commutator of position and momentum. So let x and p represent the commutator of position and momentum, and let it is operated by psi x. Then it can be written as xp minus px, and it is psi x. As eigenvalue of operator, this is equal to x, means x operator when psi, it is psi, and is similarly when p operator operates over psi, it is minus iota h cross curly over curly x psi, corresponding to x component. So keeping all these things in mind, so what I will do, it is x operator p operator psi x minus p operator x operator into psi x. So the value of x operator will remain as it is, and this p operator will be minus iota h cross curly over curly x into psi x minus iota h cross curly over curly x into x psi x. So here it can be written as minus x, and iota h cross can be taken outside. So if I take iota h cross from here outside, so it is x curly psi x over curly x with negative sign, and here minus will be positive. Oh, it is curly over curly x and x psi x. Let me try to solve it. Iota h cross minus x curly psi x over curly x plus, here I will apply the product rule, first function into derivative of second function plus second function and derivative of first function, and its value will be 1. So here this term will cancel out with it. So iota h cross psi x. Thus I can express it as xp is equal to commutator of this is equal to iota h cross. Then there is another very interesting property which I missed. Let me go back to that. This is a property, another property. I missed that property. That commutator of two Hermitian operators anti-Hermitian. That is, let us try to understand it. So an operator is said to be anti-Hermitian if, say, x is the operator, if its dagger is equal to negative of x, then it is said to be the anti-Hermitian. Now let us choose, I am having two operators and p, and they are Hermitian. That is, a dagger is equal to a and b dagger is equal to b. So now let us consider x dagger such that it is ab dagger, it is equal to ab minus ba dagger, it is b dagger, sorry, it is ba ab dagger minus ba dagger. It can be written as b dagger a dagger minus a dagger and b dagger. Since they are equal, so that means it is equal to ba. Using this, I can say that it is ba minus ab, and this is nothing but minus of x operator. Hence the result is proved. Hence the result. This is according to this statement. Then let us take another more examples. To prove that if xp square, it must be equal to 2 iota h cross p operator or 2 h cross square curly over curly x. So consider this, and this can be written as xpp, and it can be written as xp plus, from earlier identities or earlier properties of these commutators, I can write down or express this in this manner. Since its operator is equal to iota h cross its value, it is p operator iota h cross, so it is 2 iota h cross p operator, but p operator is minus iota h cross curly over curly x, so it is 2 iota h cross minus iota h cross curly over curly x. So it can be written as 2 h cross square curly over curly x. So hence it is proved. Similarly, there is another example relating to this also, is similar to this. What is the example? If I take x square comma p, its commutator, it must be equal to 2 iota h cross x operator or 2 iota h cross x. So this is equal to this x square p, it can be written as xp minus xp and it is x, so it is x iota h cross minus, sorry, it plus should be there, and plus iota h cross x, and eigenvalue of this is equal to xi. So keeping all these things in mind, this if this is a iota h cross and plus iota h cross x, so 2x 2 or 2 iota h cross x. So hence the things will be proved, right? So this is all about commutator algebra, and in the next lecture I will talk about the relationship between commutator algebra or the commutation relations with the uncertainty relation. So thanks for watching this lecture.